come originally from Cuba, that's why I have two surnames, and I work in Square for the Cash App product. So I've been focusing the last 2.5 years or so on scalability issues, infrastructure, stuff like that. Previously, I was doing consulting most of the time and working essentially on DevOps and cloud infrastructure as well.
All right, my name is Jon. Don't let the spelling confuse you. We have the same characters as you do, but we use completely different sounds when we say them. So it's not Jon, it's Jon. So I'm originally Swedish, as you can probably hear. In my 20s, I moved to London for a little while. Then I actually lived in Sydney for 10 years. But then this thing happened. So we decided to move closer to our parents and move to Berlin. We lived there for about 3-4 years. And then these two things happened at the same time. So we decided to actually move back to Sweden again. And we've been in Sweden for about 5 years, but I don't know, has anybody been to Sweden here? Have you been in winter? Oh, all right, so Sweden is a cold place, and it's very dark. So this is the middle of the day in the winter. So that's how high the sun goes in Stockholm. So I couldn't take it anymore, so we actually moved back to Sydney. So now I live in Sydney again. So I worked at these companies before, but now I work for a company called Square. You probably mostly know this product, but we work on a completely different product that you probably don't know anything about, and it's called Cash App. So it started out as being just a way to send money between individuals. And now we're starting to add more and more features like a card, ATMs, direct deposits, a bunch of stuff to essentially turn this into a fully featured bank. So it's gone reasonably well for us, and we knew we were on our success when this happened. Pokemon, us. So these days, we are usually as #1 in the finance section of the App Store, of the US App Store, I should add. It doesn't exist in Australia or Sweden, so I can't actually use the app that I'm working on. But I only deal with databases, so it doesn't really matter. And you really know you're on something when hip-hop artists are making albums about you. It's like a thing. There's like a list of 10, 20 albums that are made about our app. It's pretty cool. So it's gone well. We were originally built as a Hack Week project, running on top of a single MySQL database. And as we became more and more successful, this got bigger and bigger and bigger. And basically, this talk is about preventing this from happening. So that's what we're going to talk about today, scaling out the Cash App. So let me first set some, now I actually have to see my notes here. I can't just improvise anymore. So let me just set a bit of context for you to sort of show you the scope of the problem. So when I joined the team and started trying to tackle this problem, there was about 40 engineers that had been working for 5 years and written about 500,000 lines of code. And about in this one big database, there were about 200 tables. So we tried a bunch of things, and I'm just going to burn through these quickly, so you don't think that we just fell on this solution as our first option. So we built a little load shedding framework, so whenever we were over capacity, we could get rid of a bunch of loads so that the system and our single database could recover. Eventually, this grew into a very complex piece of machinery where we could tune different parts of the user experience to sort of find ways to navigate through a storm, essentially. We also built something called offline mode. So if the server is down, we could store up, queue up things locally, and when we came back up, we would send them off again. We moved large chunks of large tables over to key value store, which scales out better. But you can only do that because you don't have ACID transactions over your key value store. You can only do that with some tables, depending on your transactions and your transactional integrity. So in the end, you do still end up with like a core set of tables that needs to be kept together. We tried caching and replica reads, but we didn't actually get that much from that because mostly the user reads data locally. So most people use this as an app. We have a web interface as well. And then you generally read the data locally anyway. So we aren't read constrained. So these solutions, they solve for data size and read throughput. But our problem was not read throughput, it was write throughput. These don't solve for write throughput. So what do you do to solve write throughput? You can buy more expensive hardware. And we did that. We had some embarrassingly expensive pieces of hardware that ran our main database. But there's only so expensive hardware you can get. At some point, you run out of hardware to buy. You can break up the monolith, as it's called. And this is probably a good thing to do, but if you break it up into 6 or 10 parts, you get 6 or 10 times the scalability, assuming you can scale the load across them evenly. But we didn't need that. We needed 1,000 times more write throughput. So this also didn't solve the problem. So what we ended up realizing was that we had to do this thing called sharding, where you split up, you have a single system, and you split up the same database across smaller shards. We'll get into more detail later. So this is like a major event in a lot of companies' history, the sort of the moment that they realize or you have to shard. And if you worked at some of these companies, there's this mythological event in the past, usually, that happened, and which was the sharding event. It's a very scary thing to do. And to be honest, when you're faced with a problem like this, the first thing I think is, I don't actually really know how to do this. Most people don't really know how to do this. But that shouldn't, your imposter syndrome you should listen to it. It tells you to pay attention, but you shouldn't listen to it too much. It shouldn't just stop you from doing things. So with that, we started actually trying to figure out what we were going to do. And this is my section as well, right? Yeah. So we have a single database, right? So we need some way to split it up into smaller parts. So we need a way to do shard splittings, right? When we have these multiple shards, we need a way of figuring out where to send each query. So we need to be able to route our queries. We weren't originally built with sharding in mind, so we needed some ways of doing queries and transactions that span multiple shards. And with that, I'm going to leave over to Karel to tell us how to do it.
So I'll let you know how we moved on forward with these constraints. We did our research and talked to a bunch of people. We looked at the options that were available in the industry at the time, and someone mentioned, hey, you should take a look at this technology. It's called Vitess. So Vitess was built at YouTube around the year 2010, 2011. And initially, the purpose of Vitess at YouTube was to provide a protection layer for the MySQL databases, but then it grew to be like a full-scale orchestration solution on top of MySQL. At its core, Vitess is a distributed database. And when we had a look at it, we realized that it provided at least like 80% of the features that we needed. We had to just get it for the other 20%, things like, we're going to look at it later on, transactionality across multiple shards, and adapting also the solution to our own internal data centers. In 2018, Vitess joined the Cloud Native Foundation, which is an open source foundation that is hosting top quality projects that are enabling what is called Cloud Native, which are applications that are able to run in the cloud, leveraging containers, catering for massive scalability. And Vitess is currently being used, apart from YouTube, by other companies. So Slack has already presented a lot on how they scale the solution using Vitess. GitHub is considering Pinterest, etc. So the main thing that Vitess provided us was to leverage our existing knowledge in SQL, in our MySQL databases, which is where we have a strong team with lots of expertise in it. But traditionally, databases have been known to be very hard to scale, but they provide the convenience of ACID transactions and a powerful query language, which is SQL. Then around the 2000s, the NoSQL movement came up with solutions to actually provide horizontal scalability to different workloads. But in doing that, they traded off the convenience of ACID transactions and also came up with different data models for the particular use cases. A few years down the track, in the same decade, a new wave of databases called NewSQL databases came up, and they're still coming up. And they try to tackle the problem in a different way. They say you can have horizontal scalability as well as distributed transactions or ACID transactions. So we can say that Vitess is part of these type of databases, together with many others. The others, there's one called Cytos Data, which is a similar solution to Vitess for PostgreSQL. But there are many others that are worthwhile taking a look at. All right, so let's have a look at how we could roll out Vitess in an existing application. You can start, by the way, Vitess, like if you know that you're going to scale, you can start with Vitess from day one. You don't have to do what we're about to do, but we already had a very popular system that was constrained by load. So we needed to follow this approach, and it's one of the main power of Vitess. So you start with your traditional application, and you grow your database as needed. You focus on your product, and you can do the optimizations that you mentioned. You can, if you are under heavy load, you can use caching. You can use replica reads in data stores to offload the read traffic. There are lots of things that you could do, optimizing queries, etc. But at some points, your metric point at the database being the bottleneck, it is either by QPS, queries per seconds, that are related to your write load, or you are constrained by the data storage. So in that case, you can bring in Vitess in the middle. So in this step, you can have Vitess as a proxy directly to MySQL. Vitess is able to talk the MySQL protocol, but also gives you gRPC, which is the way we use it. At this point, you're already getting benefits. You're getting the benefits that originally Vitess was built for. You're getting constraint checks on the number of rows that your queries return, so you don't have unbounded queries. You're getting checks on the maximum number of bytes that you can store on a column as well. That kind of stuff, timeouts, connection pooling, which is very important. Now, the next step is, and this is the hard part, so there will be like 9 months separation before, when you have Vitess as a direct proxy to MySQL and before you're ready to shard. In our case, we had to make application changes because in a monolithic application, you probably have a data model that is similar to the one that I'm showing there, where, let's say, our data model is customer-centric, and customers can conduct transactions with credit cards or debit cards, and they have balances, which could be USD dollars or BTC. And you can decide to model your application in that way, where the transactions reference the balance, and the balance reference the customer. But that doesn't work in a sharded approach. In a sharded approach, you have to denormalize, and you have to add the customer ID. For instance, in this case, if you decide to shard by customer, you have to add it to all the tables that you decide to shard. The one that I'm showing there in blue, for instance, the merchants, is a table that is not related to the customer. So every debit card transaction, we say, is for this merchant, but you have probably a few number of merchants compared to the number of transactions. It's not part of the tables that you want to shard. And in that case, you don't need to add the customer ID. So all those things have to be taken into consideration, and it could be very challenging. For instance, you can have tables like transactions. In our case, it could be more than 1 terabyte. And how do you run a live database migration to add a column to a large table without having downtime, because you have customers paying with a debit card at the register? You cannot get a lock on that table. So we had to do lots of things and optimization to do that. It was quite challenging. But then after you sort all that, the next step, once you have Vitess as a proxy, is to do what is called a vertical split, which I think is a terminology that Vitess is moving on from, but this is actually there in the platform at the moment. That means that the data models that you decide that have to be sharded, you split your database in half. For the unsharded database, the unsharded tables, you have one database. For the sharded tables, you will have another database. So your system is going to end up having 2 databases. And all this is going to happen while the system processes transactions live in production. After you've done the vertical split, the next step then is to proceed to actually shard the database that is constrained, either by QPS or by size. This is called horizontal split. And the main things here, this is challenging as well. The main thing is to take into account that now you have to make sure that you don't have cross-shard transactions and cross-shard queries, because the more databases you have, if you have a misbehaving shard, if that operation is latency constrained or is in the critical path, you're going to have issues. So this type of things have to be taken into account. Now, let's take a look at the Vitess architecture to understand a bit more how it allows us to shard an application down the track. So you have your application. Given that Vitess is a distributed system and it also handles storage, it uses an application is called VTCFD, the Vitess Control Daemon, and that is the control plane that contains all the metadata for the cluster and the shards, etc. It's able to use Zookeeper and etcd and some other strongly consistent data storage. VTGate is the routing layer, so that's the service that your application is going to talk to, and it contains information about how to route to the right shard, or it knows how to get that information. The next important service is what is called the VT tablet, and this is a service that is paired with every MySQL instance. We deploy it as a sidecar to MySQL. This is the service also that provides a protection layer. It has the connection pooling. It checks that the number of rows that you're returning for your queries doesn't exceed a specific amount, etc. And the pairing of a MySQL instance and a VT tablet is called a tablet. And when you have a tablet with a master and multiple replicas, that is called a shard, which is a traditional thing in distributed systems like Kafka, where you have a shard that is replicated multiple times. This is exactly similar concepts. And of course, you're going to end up having multiple shards, which is what we are after. The next important process is called VT Worker, and this is the process that is going to help us actually split the data. So it's a process that is an auxiliary for the process of shard splitting. On the read side, the VTGate, when you get a query, like selecting from a customer by a specific ID, VTGate consults with the control plane, and it uses what is called the Vitess schema, which is a JSON file that specifies how your tables are going to be sharded, by which column, and by which hash function. And then based on that, it determines to which shard to route. And it could be, the table could be sharded by, columns with different names pointing to the same concept. So the instruments table, we refer to the customer ID. So the same thing gets taken into account for the routing purposes. Vitess also supports what is called scatter gather queries. So when you do like an aggregate query, it will know that it has to find out all the queries to the shards and then aggregate together back. You have to be careful with this because, like I said, when you have multiple shards, you could run into issues if it's in the critical path. On the right side, in terms of how it handles transaction, Vitess can guarantee transaction per single shard, and that's easy because it's talking to a single MySQL instance. But it also gives you what is called multi-effort, best effort transaction, where you have multi-transaction. So you define a sequence of transactions, and Vitess will make the best effort to try to apply them in that consecutive order, but you don't guarantee that the whole thing is going to be atomic. And that's the way that we use it at the moment, because 2PC, which is a feature that is present there, is still in experimental phase. Now let's see how we actually do the shard splitting. This is very important, because for us it's like I said, we have a system that is very important to our customers, and we didn't want to have any downtime. So how does Vitess help us split this database in half? So the first step, if you have a database that is terabytes of data, you need to provision the two new shards where you're going to split your database. And then you can create a new replica. So by this stage, if you're having a system that is overloaded, you already have a MySQL master and a replica to get the reads. But this is a replica that is different. It's only for sharding purposes. So it's not interfering with the production traffic at all. Then with VT Worker, we're going to start copying the data from that replica to the two shards. And that's how what is called the online clone. We copy live data that could be actually changing instead of update deletes. But Vitess is smart enough to know the next time you run an online clone, which you can run multiple times, to only apply the things that change. The next step is called offline clone, where what we need to do is, so in MySQL, when you have a master and a replica instance, you have a transaction stream. It's called the bin log. You stop replication from the master to the replica that you created, and you save Vitess saves the GTID, which is called the global transaction ID, and that's a transaction that identifies the database transaction uniquely across the entire cluster. Then VT Worker, it copies the data, only the data that changed. It doesn't start from scratch, only the data that changed since the last time we were running, and copies it over to the shard. Vitess then sets up what is called filter replication, and it's filtered because it's going to apply the routing mechanism based on the sharding column to the corresponding shard. And this replication is from the VT tablet in the source shard to the new shards that you want to provision. And at the end, after you're doing the copy to your two new shards, Vitess allows you to make sure, and this is, if you see reports from other companies that attempted to do this at the application level, you still need to do this. And the good thing is that Vitess does this automatically for us. You stop the Vitess replication and the MySQL replication, essentially nothing is moving, and then there's a comparison that happens to make sure that every data that was in the source was actually copied to the destination shard. Once you know that all the data is in the shard, the next stage is to migrate traffic. So here we have to get a downtime, but this downtime is less than 1 second, usually, because you have to wait for the shards to catch up with the Vitess replication. And when that is short, you stop the traffic. And if you're using gRPC, like in our case, it is within the bounds of our retry logic. So it's usually not user-facing the downtime. So you stop the replication to allow the shards to catch up so you stop the traffic to allow the shard to catch up with the replication. Then you migrate the traffic, and now the VTGate is going to start writing to the new two shards. And ultimately, you can decommission your old shard. So this is a high-level overview of how is it that Vitess helps you, from an operational point of view, migrate the traffic to the new shards with minimal downtime in your application.
All right, you know how Vitess works now, right? Yeah? Okay, good. So now I'll tell you what happened when we started implementing Vitess. So one thing that we introduced quickly into our code is something called entity groups, which is a way of grouping your domain model into groups that stick together during a shard split. So you know that, for example, here we have a customer and it has a payment. A pull is an attempt to pull money out of a card or a bank account. A push is a way to an attempt to push money into a bank account or a card. And you can group all these things together into the customer entity group, and the customer is the root of that entity group. And this is clear and explicit in the code, because while you're inside of an entity group, you know that that's always going to be in the same shard, in the same MySQL database, so you have strong ACID guarantees to your transactions. But if you're spanning entity groups, you don't have ACID, and now it's a scary thing. So we would actually, we could use this to sort of introspect our code, and we could have stuff in our tests that would check if we were doing a lot of co-writes, and we could figure out a way to make all of our really important code paths be safe from co-writes. But we had a problem here. So if you have a sender here, and a recipient here, you have a pull and push here, where does the payment go? So if it goes to the sender side, then you don't have ACID here. If it goes to the recipient side, you don't have ACID here. So what we ended having to do was actually split up and do this major refactoring. So payment was the core sort of entity that was in all of our code, and we had to essentially change our code completely to introduce two parts. So a sender movement and a recipient movement, and together they were sort of became a payment, sort of a virtual payment, but they were actually stored as two separate things, and they were kept up to date. So some of the data was overlapping, and they were kept up to date with asynchronously, but strongly, so eventually, but strongly consistently, they were kept out of date. So this was like a major refactoring. And we also did a bunch of other stuff. We worked on cross-shard queries. We added sharding columns everywhere, like Karel showed. We made sure that foreign keys included the sharding column. We worked on a lot of cross-shard transactions, and then we had to make Vitess work in Square's existing production environment. So all this took about a year. And in the meantime, it was about 2, 3 people working on this for about a year, and in the meantime, the rest of the team was still building functionality. So we grew the team, we added a lot of features during this time, we built the cash card, we built a lot of stuff. So it was not intrusive to, like, it was a bit intrusive, but it wasn't super intrusive. It wasn't a complete rewrite of the app. We could keep on deploying, and we would deploy several times a day as we did these changes. So that was quite nice. But in the end, we had to do it. So one November, cold November morning in Waterloo, which is a little town outside of Toronto where one of our largest offices are. Some of us had worked through the night to make this happen. So we're going to do the first vertical shard split, which is where we move the unsharded tables away from the tables that are to be sharded. And this was the scariest command line I've ever run in my career. So this essentially does this last step where we migrate the writes over to the new shard, and this is not reversible. So if this didn't work, then yeah. So I ran it, and we had a burst of errors, which fortunately dissipated. And it was all good. It was successful. We managed to split. So then we did, in December, we did a horizontal shard split. And we started noticing something here, that we got 30K QPS on the original shard. We had 20K on the new ones. So we had more QPS in total on the sharded system than we had before. So what was going on here? So the problem was that we had cross-shard queries, or the problem was cross-shard queries, right? So if you have 20K single shard queries on the original shard, and 10 of them are, and you have 10K cross-shard queries, then of course you're only going to have the single shard queries. The cross-shard queries are going to stay the same. So how do you solve this? So fortunately, Vitess has a feature called cross-shard indexes. It's called a lookup table, and so if you have a key that is not the sharding key, so you're looking for a movement by the movement ID, you're not sharding by movement ID, so it doesn't know where this shard lives, it doesn't know what the customer ID is. So fortunately, it can look this up in a separate table which mapped movement ID to customer ID, and now it knows how to turn this potentially cross-shard query into a single shard query. So using that, we could start doing more and more splits. And something sinister was happening as we were doing these splits. And this is the total sum of row locks across our fleet of databases. And when in rapid succession, we went to, every once in a while, we would have these blips, we call them, where the entire system would just lock up for 10, 20 seconds, and then everything was fine again. And these were starting to increase in frequency. And so we were worried there, and we had some people starting to dig into that and trying to figure out what it was. But unfortunately, when we did this shard split to 16 shards, the whole system just locked down. And there was just no way we could handle maybe 10% of the traffic. And as soon as we went over that, the whole thing would just lock down again. So we were hard down. So what was going on here? So the problem was, and fortunately somebody had already figured this out, was that we had distributed deadlocks. So we had, so if you have two transactions, A and B, running concurrently, so A acquires a lock on this database, and B at the same time acquires a lock on another database, and then A waits for that lock, and B waits for that lock, and now you're deadlocked. So MySQL has built-in deadlock detection. So if this happens inside a single MySQL instance, then MySQL will detect that and just roll back one of the transactions instantly. But these are two separate databases. MySQL doesn't know anything about the other database. So to MySQL, it just looks like it took a lock, and then it's just hanging around there forever, doing nothing. And of course, the reason this grew exponentially is that the probability of you having a transaction that spans multiple shards also grows exponentially with the number of shards you have. So this became increasingly a bigger problem, and in the end, when we went to 16 shards, it was essentially at like a very really high probability of this happening, depending on the traffic we had. So the whole thing locked down. The problem was cross-shard transactions. And fortunately, as I said before, somebody had already figured this out, and we actually had a pull request lined up to solve this. And the solution in this case is that we split up the transaction in multiple parts, one for each shard, and then we could resolve this. So we merged this, and the number of row locks in our system dropped instantly down, and we were actually in a better state than we had ever been. So with this in place, we could do more and more shard splits. I'm not going to get into how many we did. But you remember when we passed Pokemon Go in the top shards? So something, and we had been #1 in the finance section. So something that was starting to happen, and which is rare for finance apps, is that we were actually starting to trend in the overall charts of the App Store. So we came to number 16, number 9, number 5, and I didn't think it would ever happen in my entire life. I actually work on a product that is successful for the first time in my 20-year career. We actually made it to the number 1 in the App Store, and we didn't go down. So what have we learned here? So when your system, when you build it for 10 users, will be very, very different from the system that can handle 100 million users. So what the test gives you is that it gives you the path to get from one side to the other. So you don't have to build for 100 million users up front. You can just build for 10 users, and then you can slowly, as you progress to more and more users, and you get new and new interesting problems along the way, but it gives you sort of a repeatable process to get to 100 million users. And that's what Vitess gives you. Thank you.